Hello and welcome. Today we are going to solve a beautiful Diophantine equation. To guide our work, we'll use a structured toolkit on the right to track our key strategies. Here is our starting equation, a mix of products, cubes, and fractions. The term Diophantine is a specific instruction. We are only looking for integer solutions for x and y. Our first tool is always to simplify. We'll start by clearing that fraction. Multiplying the entire equation by 3 gives us this much cleaner, but still complex polynomial form. Note that this equation is symmetric in x and y. If you swap them, the expression remains unchanged. This symmetry is a huge clue, suggesting our second tool, using the sum, s, and product, p, of the variables. Let's formally define s as x plus y and p as x times y. The sum of cubes has a famous identity that can be rewritten purely in terms of s and p. Now let's substitute these into our equation, term by term, to see the transformation happen. First, the 3xi term becomes 3p. Next, the x cubed plus y cubed term becomes s cubed minus 3sp. This gives us an intermediate equation. Notice the positive 3p and the negative 3sp terms. We can factor out 3p from those terms, leading to our final, highly organized structure. Now we hunt for clues. Our first tool for this is number theory, specifically modular arithmetic. It's a property that n cubed has the same remainder as n when divided by 3. This means s must be a multiple of 3. This is our first critical constraint on the solution. Our next tool comes from the theory of polynomials, specifically Vieta's formulas. They tell us x and y are the roots of the quadratic t squared minus St plus p equals 0. For these roots to be real numbers, the discriminant must be non-negative. We'll call this our reality constraint. Let's begin the derivation. We start with the inequality s squared minus 4p is greater than or equal to 0. First, we need an expression for p. We can rearrange our main SP equation to isolate it. Now, we perform the crucial substitution, replacing p in our inequality with this large expression. To solve this, our first step is to clear the fraction by multiplying by 3 times 1 minus s. Expanding the terms gives us this full polynomial inequality. Now we can combine the s cubed terms to simplify the expression. Finally, by rearranging the terms and factoring out a squared, we arrive at our elegant final condition. This inequality puts a hard limit on how large s can be, but we can do better than testing values. Our most elegant tool will be an analytical search. For p to be an integer, s cubed minus 621 must be divisible by 3 times s1. Using polynomial remainder logic, this simplifies dramatically. S minus 1 must be a divisor of 60 on 20. This is a massive breakthrough. Let's prime factorize 60/20 on our canvas to see its building blocks. Now we can set up a targeted search table, checking divisors of 620 against our conditions. A divisor of 4 gives s to 5. This fails immediately because 5 is not a multiple of 3. Let's jump to a promising candidate. The number 20 is a divisor of 6020, which gives SMR 21. 21 passes both our conditions. We calculate P to be 54, and the discriminant is 225, which is 15 squared. Success! Now that we have a valid S and P, our next tool is to solve the simple quadratic to find X and Y. We must solve T squared minus 21T plus 54 equals 0. This factors nicely into T minus 18 times T minus 3 equals 0. This gives us our solutions. The integer pairs are 18, 3, and by symmetry, 3, 18. For our final step of rigor, we must verify that no negative solutions exist. A rigorous analysis shows the discriminant is always negative for S less than or equal to 3. Case closed.